Hello, my name is Julian Putnam, and today I will be discussing apoptosis and how it can be stopped due to an alteration to the phosphatase gene P10. My student ID is 1534597. I'll be breaking down the material into 4 parts. 1, how the radiation therapy used in the mouse tumor model causes a signal to be sent for apoptosis to begin. 2, what proteins are involved in cytochrome C release from the mitochondria to trigger apoptosis. 3, how cytochrome C release creates a cascade. 4, how the bad proteins are regulated and how this pathway function is altered due to P10 mutation, this leading to the unregulated cell growth. Okay, first things first, we use radiation therapy in the cancer model to break the DNA. In breaking the DNA, this triggers protein kinase activation and phosphorylation of the p53 protein. In doing this, we remove the MDM2 protein from p53. Normally, without DNA damage, the p53 stays bound to the MDM2 and is degraded by the proteasome. But in this case, since we do have DNA damage, we are going to have the p53 protein dissociate from the MDM2 after it's been activated and phosphorylated by kinase. So what we see later on is that the activated p53 now stimulates transcription of CDK regulatory proteins like p21 and many others. These regulatory proteins bind CDKs and stop the cell cycle. As we see here, P21 is created after transcription and translation of the gene, and that then binds to the CDKs and inhibits cell cycle activity. This is an example of many cell cycle checkpoints used to check a cell's viability to go into mitosis. Lastly, we notice that the apoptosis is also triggered by p53 activation. So this is a big deal because apoptosis is needed so that cells do not undergo cancer, as it is necessary for cells to die so we don't get tumor growth. So what we're going to see is that p53 signal, that apoptotic signal, is going to be sent to the mitochondria. And the mitochondria is going to in turn release cytochrome C, or these little red dots. But before we jump ahead, let's talk about the way that the mitochondria regulates cytochrome C release. So what we're going to notice is that there's going to be 3 proteins. They're going to be inside the BCL2 family proteins, and they regulate the cytochrome C response. So what we see here, these 3, we have the BCL2 proteins right here, the BH123 proteins right here in green, and we have the bad proteins, which we'll get to later. So these all here, these squares represent different BH domains within the proteins. So we have 4 in the BCL2, and that's going to be the 1, 2, 3, 4. BH123 are going to have 3, right? The 1, 2, 3. And bad is only going to have 1 of those domains. And these 2 here are pro-apoptotic, while this one is anti-apoptotic. And let's talk about what that means. So the BH123 proteins line the outside of the mitochondria right here, and these guys are trying to aggregate together to create a pore so that cytochrome C can be released from the mitochondria. However, we have BCL2 here on the outside, which is inhibiting that action. So because we have this protein here, these guys aren't aggregating together. So how does this affect apoptosis, and how does this affect cytochrome C levels then? Well, we're going to see bad come in later. So bad comes around when there's apoptosis signal being sent from p53. So what its job is to inhibit BCL2, which is inhibiting the aggregation of the BH123 proteins. And when this happens, there's like a double negative effect, right? And we're going to have the end product of aggregation of the BH123 proteins, right? And we're going to have the cytochrome C released from mitochondria, and that's going to trigger apoptosis, right? Apoptosis, again, is the goal that we want because that's what normal cells react to when we have DNA damage, right? So this is a big yay for the cell, so it doesn't go into cancer. And we don't want cancer because, you know, we're going to have a whole host of health problems because of that. So now that we've talked about cytochrome C being removed from the mitochondria, we can talk about what happens to it when it's outside. So cytochrome, when it's released, cytochrome C when it's released, binds to proteins called APF1s, and it activates them. It causes the APF1 to hydrolyze its bound ATP to an ADP, and this reveals the CAR domain of the APAF1, right? And with these CAR domains released, they can form aptosomes by having all the CAR domains associate with each other. So it forms these aptosomes by having the ADP that was now bound to this APAF1 turn or get switched out for an ATP. So now all these guys are ATP bound. Sorry for the crudeness of the drawing, but that's what happens when you're not an art major. And the aptosome now, in this form, can recruit procaspases. And these procaspases also have CAR domains, and they associate with the middle center. And these procaspases can now go and cleave executioner caspases. And cleaving executioner caspases leads to a cascade as more and more caspases cleave each other. And this cleavage will then eventually to apoptosis because executioner caspases, they cleave specific molecules that are needed for apoptosis. So again, apoptosis, my favorite little cutout, it's going to happen through this same pathway. Let's go back a couple of steps now and talk about how the overexpressed FGF affects the mitochondria's release of cytochrome C. FGF binds to a receptor tyrosine kinase here, and this activates the receptor tyrosine kinase, causing it to cross-phosphorylize itself, and in phosphorylating itself, it recruits another protein, PI3 kinase. This becomes activated when around the phosphorylated receptor tyrosine kinase, and it phosphorylates a PIP2 phospholipid head to a PIP3. So this is now 3 phosphates instead of 2. This PIP3 then can bind to PDK1 or AKT, and we'll see in the next way that the AKT and the PDK both bind to these PIP3s, and PDK1 and the protein mTOR will phosphorylate and activate the AKT protein here, which is held in place by the PIP3 until when it becomes activated through the mTOR and the PDK activity, it dissociates. And in dissociating, the activated act will then act as kinase and phosphorylate BAD, so that BAD becomes phosphorylated and it binds to a protein called 1433. And also it releases another protein, the apoptotic inhibitory protein, which becomes active. This active protein will then inhibit apoptosis, and we will get continued proliferation of the cell, and it will continue to grow. And this is important because if there is an issue with this pathway in any way, it can be detrimental to our ability to do apoptosis, right? And that's what we're going to see with the P10 mutation, where we'll talk about later, but it does cause it so the cells are not able to go in apoptosis, and they can become more cancerous than they were, and they're not able to die. Let's talk about P10. So first, we're going to be talking about the cell model before the P10 mutation, or the non-mutated P10. And this is going to be the apoptotic model, right? So when we have P10, right, it acts as a phosphatase, meaning it removes a phosphate from the PIP3 group and turns it to a PIP2 group. And in doing this, we will no longer have the recruitment and the activation of the AKT protein, and then PDK will no longer be able to bind. And with this not being able to happen, we're going to not be able to have BAD inhibited later on, which is important, right? And we're not going to get inhibition of apoptosis, and the cell is going to most likely use that BAD protein to undergo apoptosis. So we're going to look at the mutated model now here. And the mutated model is going to have P10 so that it is no longer able to dephosphorylate the PIP3. In not being able to phosphorylate the PIP3, it's going to have this PIP3 constitutively active, meaning that we are going to have continuous recruitment and activation of AKT and the use of PDK1 to act, and that's going to lead to the inactivation of BAD, which again is very important. And we're going to have continuous activation of the APOP's inhibitory protein, AIP. So we're going to go through the process of how all that affects it now. So with all that affected, we look at this here. So with the mutated model, right, we're going to have the BAD protein constitutively inhibited. With it being inhibited, it means that this is no longer going to bind to BCL2. And BCL2 is going to be constantly inhibiting the BH123 proteins, meaning they can't aggregate, and there's no cytochrome C release. Without cytochrome C release, we don't have any of these functions below happening, meaning we will not have the cleavage of executioner caspases that will lead to the cleaving of proteins and molecules required for apoptosis. And that is why our cells in the mouse tumor model, when they develop the P10 mutation, no longer undergo apoptosis, is because this BAD protein is now inhibited, meaning we can no longer go down this pathway. Okay? So that's the distinction between the mutated and the normal model. I appreciate you listening to my presentation, and I hope you liked it. Okay. Thank you.
I'm gonna jump!
Phil, get back in there!
No!
What are you doing up there?
Be reasonable!
I can't take this fucking job or those greasy shithead teenagers anymore! I'm gonna end it all!
Wait! Hold on! We're getting help for you!
Now, we know Bobby's not the killer, so who is?
I don't know.
Well, if the killer was in your house last night, why didn't he just kill you then?
Because he's just messing with us. Don't you see? He's got us right where he wants us. We can't go to the police. He's just out there watching us and waiting for us. What are you waiting for, huh? What are you waiting for? What are you waiting for?
What am I waiting for? What am I waiting for?
What are you waiting for?
You!